Hello everyone. In this module, we can discuss the probability of error calculation for optimum filter receiver. So coming to in the previous module, we have calculated the probability of error for baseband signal receiver, whereby we consider the input signal as x of t. And when it is allowed through the channel, we have assumed the added noise as n of t. So we have considered the input additive noise. So therefore, the overall signal becomes at the receiver become x of t plus n of t. Now, for example, x of t, let us consider it as a bipolar NRZ. It can be either at positive magnitude level or at negative magnitude level. And when x of t is equal to x1 of t, then r of t will be x0 1 of t plus n0 of t, where x0 1 of t represents the output signal due to the positive magnitude level of the input. And when x of t is equal to x2 of t, then r of t is x0 2 of t plus n0 of t, where x0 2 of t represents the output of output when due to the negative magnitude level of the input, that is x2. For example, if we assume that it is a noise-free environment, that is for ideal environment, r of t will be directly equal to x0 1 of t when x of t is x1 of t, that is due to the positive level of input. And for negative level of the input, r of t is x0 2 of t. In the baseband signal receiver, while calculating the probability of error, we have considered the threshold value as 0. But here we are assuming the decision boundary or the threshold as the average of the two output levels, that is x0 1 of t plus x0 2 of t by 2. Now we are going to evaluate the probability of error for both the magnitudes of input. So let us assume x of t at plus a volts, that is positive magnitude level of input. Then r of t must also be positive, that is r of t is equal to must be positive. But we know r of t is x0 1 of t plus n0 of t. But if it is negative, then error will occur. So error will occur when r of t is less than or equal to the threshold value. In this case, we consider the threshold as the average of two levels. So therefore, let us substitute r of t as x0 1 of t plus n0 of t. It is less than or equal to x0 1 of t plus x0 2 of t by 2. So take this x0 1 of capital T to the RHS. Here remember that small t is a variable and capital T is the respective instant we are evaluating the signal. Therefore, n naught of t will be less than or equal to, here you have 2 in the denominator. So take LCM here so that you will get x naught 2 of t minus x naught 1 of t by 2 in the RHS. Similarly, when x of t is at negative magnitude of the input, r of t will be h naught 2 of t plus n naught of t. Error will occur when r of t is greater than or equal to the threshold. Because when input is negative, output must also be negative. But when if it is greater than or equal to the threshold, then probability of error will arise. So x naught 2 of t plus n naught of t must be greater than or equal to the decision boundary. So take this x naught 2 of t to the right side, RHS side, as we did for earlier case. Then taking LCM, you will get n naught of t as greater than or equal to the lower cutoff you obtained, that is x naught 1 of t minus x naught 2 of t by 2. So in the figure, it's more clear to you. Here we are representing the power PSD of the output noise n naught of t. So y-axis will be the PSD and input versus the output noise component. Here we are assuming the noise as Gaussian. So that's why we have represented in the form of a bell-shaped distribution. This is a bell-shaped distribution. And here we in the last slide we have evaluated that when input is at positive level, the cutoff is at the error will occur when the noise component is less than or equal to x naught 2 of t minus x naught 1 of t by 2. So you have, in order to evaluate the error for x of t plus a, so you have to integrate from minus infinity to x naught 2 of t by x naught 2 of t minus x naught 1 of t by 2. And you have to integrate this whole PSD up to this limit. Similarly, when x of t is minus a, here we obtain n naught of t as x naught 1 of t minus x naught 2 of t by 2, greater than this. So the lower limit will be x01 of t minus x02 of t by 2, and upper limit is infinite. So you have to integrate this whole area to evaluate the probability of error for x of t is equal to minus a. So because you have assumed the Gaussian distribution function for n naught of t, fx of n naught of t can be represented as 1 by sigma root 2 pi e power minus of n naught of t whole square by 2 sigma square, because here we have assumed mean as 0, where sigma represents the standard deviation and sigma square represents the variance. Now we are going to calculate the probability of error when x of t is equal to minus a. And in the figure you observe that you have to integrate the whole area beyond x01 of t minus x02 of t by 2 to evaluate the probability of error for negative magnitude of input. So that's why you have taken the lower limit as x01 of t minus x02 of t by 2 and upper limit as infinite, with the signal fx of n0 of t as 1 by sigma root 2 by e power minus of n0 of t whole square by 2 sigma square. Just be substituted here, and now you are going to integrate. And before proceeding with the integration, for simplification, we have assumed this exponential power factor as some y square, so that you can write it in the form of complementary error function. So let us assume n naught of t whole square by 2 sigma square as y, and rewrite this whole integration in the form of y. So as usual, we assumed y square as n naught of t whole square by 2 sigma square. So y will be root of this whole. So n naught of t by sigma root 2 you will get. And accordingly the limits also will change. So dn naught of t will be sigma root 2 into dy. And coming to the upper limit, when n naught of t is infinite, y will also be infinite. But the lower limit is when n naught of t is x01 of t minus x02 of t by 2. You will have y as x01 of t minus x02 of t by 2 root 2 sigma, because denominator you have sigma root 2. Let us substitute all these factors in terms of y in the probability of error expression. So that integral lower limit is x01 of t minus x02 of t by 2 root 2 sigma, and upper limit is as usual infinite. And the function is 1 by sigma root 2 pi. And we have replaced y square. So e power minus y square into dn naught of t will be sigma root 2 dy. And but complementary error function ERFC of u can be represented as 2 by root pi integral u to infinite e power minus y square dy. Now we are going to represent the PE expression in terms of ERFC of u. So upon simplification, here you can observe that sigma root 2 and sigma root 2 gets cancelled, and you will have 1 by root pi here. But to represent in the form of complementary error function, you should have 2 by root pi. So multiplying and dividing with respect to 2, you can write the probability of error expression as half ERFC of x01 of t minus x02 of t by sigma, where x01 of t minus x02 of t by sigma represents the output SNR. So this is the probability of error for negative magnitude of input. Similarly, for positive magnitude of input, you have to integrate the whole area from minus infinite to minus infinite to this limit, that is x02 of t minus x01 of t by 2. So in that case also, you will get the probability of error as expression as same as that of the probability of expression for negative magnitude of input, that is half ERFC of x01 of t minus x02 of t by 2 root 2 sigma. Here remember that this x01 of t minus x02 of t by sigma represents the output SNR. So if there is any increase in the output SNR, obviously the probability of error will reduce, because this function is a complementary error function. In the next module, we can discuss with the calculation of SNR of optimum filter receiver. Thank you for listening.